start. So what were we discussing? I think we are at the end of this chapter, right? Okay. Just close the door. Yep. Shall we proceed? So from yesterday's topic, you have any doubt in dimensional analysis, its applications? So now you know what is the dimensional formula, right? Let's just recollect before we start. What is the dimensional formula? For a physical quantity, especially derived physical quantities, you will be able to write the mathematical expression for it in terms of symbols of known parameters, right? So what are the known parameters we are trying to talk about? The 7 fundamental quantities. So if you're able to write how many times the physical quantity is dependent on those fundamental quantities raised to the power of something, right? Then that formula is called as dimensional formula, and the powers are called as dimensions, right? So why is dimensional formula or dimensional analysis useful for us? How is it useful? First is to check or to derive a physical quantity from one system to another, right? Second is to verify the dimensional consistency of an equation. And the third is to derive a mathematical expression for a physical quantity when we know how it is dependent on the other physical quantities. That was the last topic that we did yesterday. Okay. Just to make our brains active, can we try out for one more physical quantity? So can you derive the formula for another physical quantity today? Write it down. Using dimensional analysis, derive a mathematical expression for T, that is the time period of a simple pendulum where it is dependent on length and acceleration due to gravity. L stands for length. Those who are online, are you able to hear me?
Yes, sir.
Yeah, and G stands for acceleration due to gravity. Can you try this? Exactly 5 minutes time, try it out. So T is directly proportional to L power A. We already got the value. T is directly proportional to L power A. That's right. Anybody with the answer? No? So shall we see how to do this? Time period is, what did you get? L square B. So T is directly proportional to L power A and T is directly proportional to G power B also. Yes. So I can say T is directly proportional to L power A into G power B, which implies T is equal to K times L power A into G power B. For dimensional consistency. By the way, did you all write the name outside? You all wrote? While coming, did you write your name? You wrote it up? Okay. Then absent and trigger again, your parents will get tensed. For dimensional consistency, dimensional formula of T is equal to dimensional formula of L power A into the dimensional formula of G power B. Right? So dimensional formula of T is T, or can I write it as M0 L0 T0? Sorry, M0 L0 T1 is equal to, what is the dimensional formula of L? Only L. So L power A. The dimensional formula of G is LT minus 2 to the power B. So what do I get? L power A plus B into T power minus 2B is M0 L0 T1. So here it is going to be M0. Then what about A plus B? A plus B is 0, which implies A is equal to minus B. So minus 2B is 1, which implies B is equal to minus half. So when B is minus half, A is equal to half. Right? So T will be equal to K times L power half into G power minus half. So this will be equal to K into square root of L divided by G. And this is the mathematical expression. And this is called as the time period of a simple pendulum. Okay, where the value of K is equal to 2 pi, which we cannot find it dimensionally, only we can find it experimentally. Okay. So the actual formula is T is equal to 2 pi into root of L divided by G. Right? Clear? So with this, we have done the dimensional analysis part. We will see the disadvantages of it. Shall I proceed? Yeah. Those who are online, shall I proceed? Clear?
Yes, sir.
So listen, the limitations that are in the dimensional analysis are in any dimensional formula containing M, L, and T, we get at the most three equations by equating the powers of M, L, and T. Hence, dimensional analysis cannot be used to derive the exact form of physical relation if a physical quantity depends upon more than three physical quantities. So, in any dimensional formula containing M, L, and T, so that is mass, length, and time, how many physical quantities are there? Three. If at all you want to derive the mathematical expression for a physical quantity which is dependent on M, L, T, you cannot derive it if it is dependent on a fourth quantity. Means if it crosses three quantities, you will not be able to derive the dimensional formula. Sorry, only three quantities you can do it. No, I'm not saying only these three. It is like three physical quantities maximum. If it crosses that, it will be difficult for you to derive it. Okay, that is one thing. Second is information about the dimensionless constant that you are introducing. For example, in the previous derivation also introduced K. And what is the final expression? We got K into root L by G. So, information regarding the dimensionless constant cannot be obtained at all. For example, T is equal to K into root L by G, where K is equal to 2 pi can only be obtained with the help of experiment. Okay. And third is dimensional analysis cannot be used to derive expressions which involve trigonometrical, exponential, and logarithmic functions. Okay. So wherever there is a physical quantity which is actually dependent on trigonometric quantities, exponential quantities, and logarithmic quantities, you cannot derive the mathematical expression for them using dimensional analysis. For example, you have work done, right? So what is work done? What is that you have learned work done as? Force into, you have learned this, right? Force into displacement. Did you? At least you remember something like this. But actual formula is not force into displacement alone. If it is actually Fs cos theta. Fs cos theta, where F stands for force, S stands for displacement, and cos theta stands for the angle between force and displacement, which we'll be learning this year. Why they didn't teach it in 9th standard? Because you didn't have trigonometry in the first place, and that is the reason why they didn't ask you problems also where the force and the displacement were acting in different directions. So that is why the formula was only taught as force into displacement. But the actual formula is Fs cos theta. So if you want to derive this expression using dimensional analysis, will you be able to do it? Why? Because for dimensional consistency, what are we doing? We write dimensional consistency, we write dimensional formula of W is equal to dimensional formula of F into the dimensional formula of S. This is what we are doing. But if I put the dimensional formula of cos theta, there is nothing. Because cos theta is a number. Cos 30 is root 3 by 2. It's a number. Cos half, so 60 half is a number. So for a number, you don't have any dimensional formula available. If that is the case, we will not know whether the physical quantity is dependent on the trigonometric function or not. So that is one of the disadvantages. Okay. For this method is again not useful in the places where the constant that you are introducing, right? In the places where the constant that we introduce is not dimensionless. So if at all you have a formula, for example, F is equal to G M1 M2 divided by R square is there. The G is what? It is a universal gravitational constant. But if you see, This universal gravitational constant is not a dimensionless quantity. When I say dimensionless, the meaning should be m0, l0, t0. That will happen only for a number or a constant. Okay. Whereas the g is there, no, it has a dimensional formula with it. If that is the case, then you cannot derive this formula using dimensional analysis. Is that clear? So these are all the drawbacks. So I'll give you 5 minutes time. Make a note of all these things. Just exactly copy the points. Is it visible? You're able to see it? Okay, write it. So the heading would be limitations of dimensional analysis. Limitations of dimensional analysis. So if the first point is over del V, I'll slightly move it up. So done with all the points. 4 points are over. Huh? So these are the limitations with respect to dimensional analysis. And major part of the chapter is over. Okay. One last topic that we are supposed to discuss is significant figures, because that is the mathematical part. Apart from that, everything else is theory only. I told you about the parallax method and all those things, right? That I will explain it later. Okay. Shall I proceed? Yeah. Yeah. Those are online notes. I hope you have written it. Okay. So listen. So the next topic that we are going to discuss is called as significant figures. Write on this heading. Significant figures. First, let us try to understand the book definition of it. What does it say? So figures here represents numbers. So significant means, what do you mean by significant? Something which is important. Right? You say something which is significant. So here, when you take a measurement, for a measurement, obviously you are going to report the answer in terms of some numbers. Where the numbers generally we call them as digits, or you call them as figures. Right? So out of the numbers in which you try to report the answer, how many digits are significant and how many are insignificant is what we are going to see in this topic. Is the point here, right? So first write down the definition. The number of digits in a measurement. The number of digits in a measurement about which we are certain. The number of digits in a measurement about which we are certain. What do you mean by certain? We are sure, right? About which we are certain, plus one additional digit, plus one additional digit, which is uncertain. Which is uncertain is known as, are known as significant figures. Okay, now let's read the definition again. What you say? In a measurement, you have number of digits. Out of the number of digits, whichever we are certain, plus the last digit which we are uncertain, plus one additional digit. Not like you can add any number of uncertain numbers you want. There's one uncertain number you are allowed to add. If you do that, then the final answer that you're reporting is going to tell you contains how many significant figures in it. Okay. Now again, coming back to the point, why do we need significant figures in a measurement is again something related to accuracy and precision. Okay. For example, if I give you a reading, I'll take a simple example for that matter. So if I ask you to measure the length of an object, right? So you guys are in school, right? You go to school, and I say I want you to measure the length of something and tell me, right? What is the tool you are going to use? You use the 15 centimeter scale because that is easier for you to carry. You use that. Is that right? So when you measure it, for example, I give you this pencil and I ask you to measure the length of it. What will you do? You will go inside the zero here and you take the measurement. So when you're taking the measurement, one end, yes, it is in your hand where you can exactly coincide with zero, but the other end is not in your hands, right? On the other end, let's say your reading falls somewhere between 10.2 and 10.3. So it is falling somewhere between 10.2 and 10.3. Then if I ask you to report the exact answer to me, what will you do? You would say the answer is neither 10.2 nor 10.3. So what should it be? You will see where is that endpoint closer to. If it is closer to 10.2, you will approximately tell me it is a 10.2 centimeter length. If it is closer to 10.3, you will say it is 10.3. If it is somewhere in between, then you will say 10.25, which is also not accurate about this, right? So when that is the case, when you report the answer as 10.25, for example, you're telling this to me. Okay. Out of the 4 digits that you are able to see, 4 figures that you are able to see, how many are certain? 10.2 is certain, but that 5 you are uncertain. Is that right? So it is only your guess. So if I ask you how many significant figures are there in this scenario, what will you tell me? You will say 4, right? But if I give you a measuring device which is able to exactly tell you about 10.25, then you are going to be more accurate and more precise, right? So what does precision have to tell about the number of significant figures? For my reading to be to the best precision possible, do I need to have more number of significant figures or less? If I have more number of significant figures, then I can say my reading is more precise because I have an instrument. Precision is related to whom? Accuracy is related to you, we who take the measurement. Precision is related to the instrument which is helping us take the measurement. So if you are able to report the answer to more number of decimal values, you can say that particular reading is more precise. Means if more is the number of significant figures present in a particular reading, more precise your answer is. Is that clear? So you are able to understand why we are reading significant figures. It is mainly to speak about the precision of a particular measurement. Okay. So this is the basic outline. If you want, you can make a note of the point which I told you. Significant figures are mainly read to understand or mainly studied, you can say. So significant figures are mainly studied to understand the precision of a particular reading. Water. Okay, so it's the same example that is considered here. Suppose you are measuring the length of the pencil. Keep one end of the pencil on the 0 scale of the meter, and suppose the other end is between 12.3 and 12.4, depending on where the least. So what happens to the least scale? Least count of the scale that you have in your hand? It is 1 millimeter or 0.1 centimeter, right? When you do this, you cannot tell whether the answer is exactly 12.3 or 12.4. So what you do, you round it off to somewhere around 12.38, for example. If you do this, then we are certain about the digits 1, 2, and 3, but uncertain about the digit 8. So number of significant figures is 4. Okay. So am I clear till this point? right? The next part is about understanding the rules of determining the number of significant figures. There are certain rules. Okay, we'll try to make a note of it. Okay. First, all the non-zero digits. So you have all the non-zero digits, then they are significant. Please make a note of it. So along with the explanation, I want you all to write it also. First point is, so write on the heading as rules for determining number of significant figures. First, all non-zero digits are significant. For example, in measurement of mass, suppose the answer is 125.63, so which is reported in terms of grams. Okay, 125.63 gram, which has 5 significant figures. What are they? 1, 2, 3, and 1, 2, 5, and 16. Right. So the only problem starts when zeros are there. Now the question is, when will you take that zero as a significant figure? So means what should be the position of that zero for it to be considered as a significant figure, and what should be the position where it is considered to be an insignificant figure? It is not considered at all. First, if you have two non-zero digits, okay, let's say 1 and 5, between them you introduce how many ever zeros you want. All those zeros are considered to be significant because the starting number, for example, I have 1 and a 5. If I introduce 1 0, it becomes 105. It contains 3 significant figures, 1, 0, and 5. If I introduce 2 zeros, 1005, 1005. So those 2 zeros are also significant. 3 zeros, significant. Like this, any number of zeros that I introduce between two non-zero digits are always significant. Right now, make a note of it. All the zeros between two non-zero digits, all the zeros between two non-zero digits are significant. Comma, no matter where the decimal point is. So if at all there is a decimal point present, no matter where the decimal point is. Those who are online, are you able to understand what I'm saying?
Sir.
Yes.
Okay. See, for example, this 125.004 is there, right? If I want to shift the decimal value to two values to the left, 1.25004, still the number of significant figures are 6. Okay. What happens if the decimal point is before a non-zero digit? That is the next story that we will see later. Okay. So first digit is non-zero, last digit is non-zero. In between, how many other zeros are there? They are significant. Third, if the number is less than 1, first we'll stop it here. If the number is generally when it is less than 1, then what will be the starting number of it? 0. So for example, 1 by 2 is there, less than 1, 0.5, 1 by 3, 0.33. So the number before the decimal will always be a 0, but the number after the decimal will generally, assuming it to be generally it will be a non-zero number. Okay. So listen, if the number is less than 1, then the 0 that is present on the right of the decimal point, but to the left of the non-zero decimal are insignificant. Okay, so listen to this. If the number is less than 1, then the zeros on the right of the decimal point, but to the left of the first non-zero digit are not significant. Okay. So what is the meaning of it? For example, I have a reading like this, 0.0001507. Okay. So it started with 0, right? So 0 point, you can think that why are we ignoring the zeros that are there after the decimal point? So the zeros that are there after the decimal point also, but the zeros which are there before the first non-zero digit are always considered to be not significant. So how many significant figures are there in this? Only 4. What are they? 1, 5, 0, and 7. There is a 0 in between 5 and 7. That is significant. But the ones before 1 are insignificant because are not significant for that matter. Why? Because if I write something as 0.0015, For example, it is a meter. Then I can write the same thing as 0.000015 centimeter. Oh, sorry, 0.15. So this will be 0.0015 into 10 power 2. 1 meter is 10 power 2 centimeter. Yeah. So I can write it as 0.15 centimeter. Is the point clear? So what is that? So 0.0015 meter and 0.15 centimeter. If you see, what are the two significant figures in it? It is only 15. So there are only two. Now you are able to understand why the zeros that are there before the first non-zero digit are ignored. Because when you write from one unit to another, the zeros that are present before the non-zero digits don't add any value. So here, what is the important number? 15 only. Is the point clear? So this is the reason why we consider them to be not significant. Okay. Suppose I have a number without a decimal point. So in a number without decimal point, the zeros on the right side of the last non-zero digit are again not significant. Right? In a number without a decimal point, the zeros on the right side, of the last non-zero digit are not significant. Please make a note of it. Why? So let's see. Let's take the same example. 132 meter. Okay. This will become 13200 centimeter. 132,000 millimeter. It keeps on going like this. If you want to write it in micrometer, you will add 6 zeros. So when you do it, what is happening? Are those zeros important for us? No, because you are adding those zeros only because you are converting them from one system to another. For example, the first case is an SA system or MKS system, then you are converting it to a CGS system. When you do this change, it is at 132 that is important for me, not those two zeros. For example, had the reading been something like this, 132001, now will those zeros be significant? Yes, because they are between two non-zero digits. So the zeros which are taken after the last non-zero digits are not important for us. And the reason being, when you write it, those zeros will get added only because of the fact that you try to convert the number from one system of unit to another system of unit. Clear? Fifth one. The trailing zero. So previous one that you saw, the zeros that are added without a decimal point. But if the same number is with a decimal point, see what will happen to the zeros after the non-zero digits. The trailing zero or zeros in a number with a decimal point are significant. The trailing zeros means the zeros which are there after the non-zero digit, provided the number has a decimal point, are what? Significant. This is a very, very important point. Are you able to differentiate between fourth and fifth? So in the fourth also you are saying zeros after the non-zero digit, but in fifth also you are saying the zeros after the non-zero digit. In fourth case, you are not considering it to be important. They are not significant. Whereas in the fifth one, you are saying they are important. Why? So what does a decimal point have to tell us? Just because there is a decimal point, you mean to say they are important? Is that the reason? Not? Non-zero. See, for example, I have 7900. How many significant figures are there? 2. That's what the fourth point says. If it is a non-decimal number, then the zeros after the last non-zero digits are not significant. Whereas if I make the same reading as 7, if I add a point, those zeros are becoming important for us. Okay, I'll make it even more simple. 790, 7.90. So 790 also has 2, but 7.90 has 3. Why is that 0 suddenly becoming important just because I added a decimal value? It is more precise. Is that what you're trying to say? Why is it so? Because you're adding more number of decimal values. That's right. So if you see, when you write the answer as, for example, even if you write the answer as 7.00, right? Those two zeros are important. You know why? Because when you say 7.00 is one of your readings, the next reading might not be 7.00. It will be 7.01. It might be 7.10. But what does every reading tell you? Means in your hand, you have a measuring device that is able to measure up to 2 decimal values. Whereas 7.00, if you write the answer as 7 and leave it, if somebody wants to continue the experiment that you're doing, what will they write? They'll round it off. The 7.01 also has 7. This will also be rounded off to 7. Means you're trying to report only for one value. So those two values are important for you. So those two zeros are like two blank spaces where you're saying the person has to report those two blank spaces also to me. That is why those zeros are important. For example, if I write 7.910, means I'm trying to say that in my next reading, if I have something greater than 91, if I get a non-zero number at the end, I need to report it. Then this is more precise. That is why in the case of decimal, the zeros which are occurring at the end of non-zero digit are important. Whereas in the case of non-decimal number, they are not important. Is it clear? So this is one of the places where I've seen people making mistake. They want this to get registered in your mind. Is it clear? Now we'll do a combination. 7.900 and 0.007900 and 0.7900. So how many are there in this? 4. How many are there in this? There are 6. So what are the 6? 007900. But actually it is 4. Because what does the second point tell you? When you have a decimal number, the zeros before the first non-zero number are also insignificant. So here also you have only 4, and here also the third one also you have only 4. Is it clear? Right. The next question is, when you take the measurements, like how you had the combinations of physical quantities, so there might be a physical quantity which is some difference, product, or division of two other physical quantities. Whenever you come across those kind of scenarios, how are you supposed to, how many significant figures are you supposed to report is what we are going to see now. Okay. So write down the heading as significant figures in addition, subtraction, multiplication, and division. Right. So when you talk about any physics experiment, generally what will happen, it involves multiple measurements that you need to take, and to your best knowledge, you will always try to report the answer to the best accuracy and precision possible. Right. So when I say precise, you need to be clear about the number of significant figures. Okay. So, but for my measuring device to be more precise, what should happen to the least count of it? You have heard this word least count, right? So what is the meaning of least count? the least value, the least distance between two subsequent lines is what is called as least count. For example, the scale that you're using has a least count of how much value? 0.1 centimeter or 1 millimeter, right? So least count of a measuring instrument. Suppose you have the resistance of different resistors. So last year you learned this thing. If I give you two resistors, R1 and R2, and I ask you to connect them in series, what will be the final resistance? We add R1 plus R2, right? Suppose you have a separate resistor in your hand, R1. You're separately measuring the value for R1 and you're reporting the value of R1 as 5.67. Suppose I'm like 1, 2, 3, 4. You 6 of you are there, okay? I'm each of you, I'm giving you one resistor. And 3 more were online. So I'll give you 9 resistors individually. And I say, individually, you guys measure and tell me what is the value of R1, R2, R3, R4, R5, till R9. Okay, 9 of you will give me the values. Then what will I do theoretically to find the rest? When I connect all those resistors in series, I'll try to find out what would be my equivalent resistance. Okay. Suppose the first person who comes and tells me, sir, the reading for the resistor that you gave me is 5.67. Okay, I took it. Okay, collected it back. The second person comes and tells me, sir, the resistance value is 12.345. And the third person comes and tells me it is 0.7. Like this, I'm getting all the 9 values. Okay. But if you observe something in the readings that come to me, there is some kind of inconsistency I'm able to find. What is the inconsistency? The first person who reported the answer to me has reported only till 2 decimal values. The second person has reported the answer to me for 3 decimal values. And the third person has reported only till 1 decimal value. It could have been because of laziness also. Right? So when that is the case, when I find the equivalent resistance, when I add all the values, sometimes what will happen, I'm adding a 2-digit number to a 3-digit number to a 1-digit number. When I do this, I'll get a final output. And the final output will give me till how many digits? So out of these 3 readings, which one has the highest number of digits after the decimal value? Second one. So when I add everything, I'll get the reading till 3 decimal values. Okay. But how should I report my answer? Should I tell my answer is 18.715? Guys, are you able to understand the context? So 5.67 means 5.670. 12.345. 0.700. If you observe, the person who reported 0.7 to me didn't say 00 about it. They didn't say 00. Means he has taken a measurement only till 1 decimal value. I'm adding those 2 zeros. So those 2 zeros are not significant. I don't know what it is. I'm just adding it for the sake of mathematical purpose. When I do this, I'm able to see that the answer comes out to be 18.715 ohm. But out of these numbers, which one is certain? No, certain in the sense, this number 18.715 is there, right? I got the answer till 3 decimal values. So should I go and tell someone that if you add all those resistors in series, if you keep them in series, you will get this value? You know, I'm not sure. So what should I report? I'm not sure because who's the culprit there? Who's the culprit among all the 3? First one or last one? Last one, because he was the laziest guy. So he spoiled my reading, correct? So this last reading, what I am forced to do is, I can't report my answer as 18.755. Rather, I should report it only till 1 decimal value. I'll tell my answer is only 18.7. Because of him, I need to restrict my reading because I'm not certain about what are the other 2 digits. This guy gave me an accurate reading, 12.345, but the other 2, okay, that is also somewhat true, but 0.7, he has missed 2 significant figures. So I need to report the answer, the final answer in the less number of significant figures possible. Only then my answer will be accurate. Are you able to understand what I'm trying to say? So the answer that you're going to report will not be 18.715, rather you will report it only as 18.7. So when you're adding two numbers, right, to conclude the whole story, when you're adding two numbers, you get a final number, right? Especially when you have decimal values, right? When you get that final number, you should report the answer to only those decimal points by taking the reading which has the least number of decimal points in consideration and report it. So in this case, it is only till one decimal value, that is 0.7. So I didn't report that 1.5, I stopped it with 7. For example, R3 was not there. Had there been only R1 and R2, then I would have reported my answer for 2 decimal values. Suppose everyone gave me the three decimal values, then I would have very well done with 3 decimal values also. Okay. So when you're doing addition or subtraction, you should always report the answer to the least decimal values that are there in the readings list. Okay. So please make a note of this. Whatever story you have understood, write it. So first write down these values. R1 is 5.67, R2 is 12.345, and R3 is 0.7 ohm. So when they are connected in series, okay. In this problem, you see, I report answer as 18.7 and not 18.8 because, so till here you understood, you need to report only till one decimal value. What is the decimal value supposed to be is decided by an other tool called as rounding off. So you know what is rounding off, right? So when I ask you to round up the number, you just try to reduce it to, you will reduce the number of decimal places, that's it. So why did I stop and write it as 18.7 and not 18.8? Because after 7, I looked at the number. After 7, what do I have? 1. So 1 is closer to 0 or 9. Which one is it? So if I take a scale like this, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, the next number would have been 18.8. So 1 is closer to 0. So I wrote the same number, 18.7. 18.7. Had it been, had the reading been 18.795, then I would have rounded off my answer to 18.8. This tool is called as rounding. Okay. About that, we are going to see now. So that is why, if you see, if any result with more than one insignificant figure. So in this case, how many insignificant figures do you have? 2. 1 and 5, both are insignificant. Because when you added all the digits, you got 18.715, 1 and 5, both are insignificant. If there are more than 2 insignificant figures present in a reading, then you need to follow the process of rounding off. So for rounding off also, you have certain rules to be followed. Okay. For this purpose, so I'm reading this reason. Thus, any result with more than one insignificant or uncertain digit should be rounded off up to the current number of significant figures. For this, there are certain rules that we are going to follow. The first rule is, if the insignificant figure to be dropped in the sense which is to be ignored. If the insignificant digit to be dropped is less than 5. So how did I find the insignificant figure in my 18.715? This is my insignificant figure. I need to drop all the values after that. So if I need to drop the number and that number is less than 5, then what will you write? If the number is less than 5, then the preceding digit is left unchanged. So that is why if you see, I didn't disturb 18.7 at all. I left it as it is. So the number to be dropped is 1. Since 1 is less than 5, the preceding number to it. What is the preceding number of 1? 7. So I left 7 as it is and reported the answer as 18.7 ohm. Is that point clear? Right? Please make a note of this. So you can write the heading as rules to round off. Rules to round off. Okay, first one, what does it say? If the insignificant figure to be dropped is less than 5, then the preceding number is left unchanged. Then the preceding number is left unchanged. Okay? Is that point clear? Second one, now you can guess automatically. If the insignificant figure to be dropped is greater than 5, then what will you do to the preceding number? For example, it is 18.765. Had it been 18.765, I want you to drop the numbers after 6. So before 6, you will see the preceding number. 6 is greater than 5. So you'll add +1. So what would have been your answer? 18.8. Okay. If the digit to be dropped is more than 5, then the preceding digit is increased by 1. Is that clear? And the preceding digit is increased by 1. So we saw two important things. What is it? The numbers to be dropped are less than 5 and greater than 5. So what is the checkpoint here? 5. If the number to be dropped is 5 itself, then what are we supposed to do? No. That is when you will see whether the preceding number is even or odd. Okay. Listen. If the digit to be dropped is 5 itself, then the preceding digit is increased by 1 if the preceding digit is an odd number. For example, 18.755 or 759. For example, I'm just taking. I want you to drop after 5. So I want you to drop that 5. So what should you do? You should look at the number preceding it. If the preceding number is an odd number, then you increase the value by 1. So you write it as 18.8. Whereas if it is an even number, for example, you have 18.659. I want you to drop this 5. If it is an even number, then the number is left unchanged. Means what will you write the answer as? 18.66. Is it clear? If the digit to be dropped is 5, then the preceding digit is increased by 1. If it is increased by 1, if it is odd, and is left unchanged if it is even. Is it clear? This is the technique used in rounding. Can you close it by tomorrow morning? Close it. This is fundamental unit of life and life process. I've already told you. Here is right. So again, there are some more rules. We'll see that. So when you talk about addition and subtraction, right, this we have already seen. Just summarizing. The following part should be observed by carrying out the addition or subtraction of two significant numbers. If all the numbers are integers, okay, all the numbers are integer, the summation or difference, right, or subtraction. See, there is a small difference between difference and subtraction. I think I've told this. Difference between 1 and 2 is 1. Subtraction of 1 and 2 is -1. So be careful with that. Okay. So if all the numbers are integers, the summation or subtraction should be carried out in a normal way. So we have no problem. Right. Whereas when you have these decimal values, in addition or subtraction, the final result should retain as many decimal places as that are there with the number of least decimal places. So this is the reason why that 1,5 was dropped. Right. That is with respect to addition and subtraction. I hope this point is clear. Right. Then what about multiplication and division? So when you talk about multiplication and division, in any measurement, the last digit is generally considered to be uncertain. Generally, whenever you take any measurement, the last number is generally considered to be uncertain. Multiplication of any number with the least significant digit is also insignificant. So when you multiply, what will you do? For example, I have reading 12.13 and 15.245. So last digit here, 3 is uncertain, and the last digit here, 5 is uncertain. So when you multiply these two numbers, you are multiplying those uncertain numbers also. You multiply the 3 and 5 also. Is that right? So when you do that, that is what they're trying to say. Multiplying of any number with least significant digit is also insignificant. But the final result should contain only one insignificant digit. That is what the definition of significant figures tells us. If you go and revisit the definition again, what does it tell? Significant figures are basically the numbers which are certain plus one uncertain digit. That is one insignificant digit is allowed. You are allowed to write. Okay. Therefore, when you're doing this multiplication or division process, these are the following steps to be kept in your mind. First, in multiplication or in division, the final result should retain as many significant as that are there in the original number with least significant. Again, suppose you have the length and breadth of a rectangular plate, okay, which is 2.613 and 1.2 centimeter. Then you are getting the answer as 3.1356 centimeters square. That is the area of the rectangular plate. But how will you report the answer? So read that first point. In multiplication or division, the final result, that is 3.1356, should retain as many significant as that are there in the original number with the least significant values. So out of 2.613 and 1.2, which has least significant? 1.2. So you should round off this 3.1356 to one decimal value. When you round it off to one decimal value, what will be the answer? It will be 3.1 or 3.2? 1 only. Because what are the numbers you're dropping? You're dropping after 3. So if the numbers are less than 5, the preceding number is left unchanged. So answer will be 3.1 centimeters. You're able to see this? You understood why you're dropping the first place? Because the last digits are insignificant. So you can't say that is an accurate reading. But 3.1, yes, you're sure. 3.1 centimeters square. Suppose you have the division of two physical quantities. For example, let's say the mass of an object is 3.523 gram and volume is 1.47 centimeter cube. Suppose you want to find the density of that substance. What is the density? Mass by volume. So mass is 3.523 and the volume is 1.47. Is it right? So when you do this, you get the answer, for example, as 2.429665552. Right? You have done it till this value, but I want to write only the rounded off answer. So I'm looking at those two readings. Out of those two readings, which is least significant? Which has the less number of significant figures? 1.47. So I'll stop my value to 2 decimal values. So 2.42, I'll drop from 9. Since 9 is a number greater than 5, I'll round out the preceding number by adding plus 1. So answer would be 2.43 gram per centimeter. Are the rules clear? Clear? So this is what you're supposed to do. Right? And the same logic is applicable for other branches of science as well. So mainly measurement has nothing to do with physics, chemistry or math, or physics, chemistry, biology. It is the same with other parts as well. Okay. And mainly you're doing all these things only for the sake of your record book. When you're taking the measurements, right, you're mainly doing practicals only to understand how to maintain accuracy. It's not about getting the answers. Whatever answer you got, it's to improve your knowledge of how accurate your measurements are. For that, there are two things needed. One is you should be careful, and the second thing is you should have a clear-cut understanding of the devices that you are using at the lab. Just because they gave you something, don't just take it and start doing. You try to analyze and figure out why we are using this. Then you will understand and it will be easy for you. Okay. So has the practical started for you? No, right? If at all it starts, right, I'll suggest you a website. There is a website called OLabs. OLABS. There is a website called OLabs. OLO lab. Laboratory. So labs. Laboratory. Yeah. So OLabs, which is developed by Amrita University, where simulations are available. So you will have, for whatever experiment that is there in your syllabus, you have simulations there. Simulations in the sense you can enter dummy value and check it. Based on that, the animation will go accordingly. Okay, that will help you to do things faster. They also have some pre-recorded videos also, which will guide you to say that yes, these are all this is how you perform the experiment. You can make use of it. It is 2.42566. For example, had it been, this is what you're asking, 2.425665. You want to drop this. The number you want to drop is 5. Preceding number is an even number. So you leave it unchanged. So 2.42 gram per second. Okay. So we'll start with some simple problems. 12th one. The number of significant figures in. So you can just write down the number of this. Okay, I'll share this assignment with you. So number 12th one. The number of significant figures in 5.055 and 0.005055 are. In the first one, how many are there? 4. In the second one also, you have 4. One common mistake that you will do is you write it as 6. But why not? Why is it not 6? Because the zeros before the first non-zero digits are not significant. So 5055. So answer is 4 and 4. What about the 13th one? The number of significant figures is figures in 0.0060. The zeros before 6 are not significant, but the 0 after the 6 is significant. So answer is 2. Okay. 14th one. The gravitational force between the masses m1 and m2 separated by distance r is given by F is equal to g m1 m2 divided by r square, where g is the universal gravitational constant. Then what are the dimensions of g? 2 minutes time, write out. You have to use the dimensional consistency. M1 and M2 are masses. R is the distance. So F is equal to Gm1 into divided by R square. So dimensional formula of F is equal to dimensional formula of G into dimensional formula of M1 into dimensional formula of M2 divided by the dimensional formula of R square. So what is the dimensional formula of G? This dimensional formula of F into dimensional formula of R square. You understood what happened? This quantity went this side, and M1 and M2, which were in the product, came out as division. So the dimensional formula of F is MLT minus 2, and the dimensional formula of R square is L square divided by the dimensional formula of M1 into M2 is M square. So 1M got cancelled. You have M minus 1 L cube T minus 2. Is that clear? So is there an option in the first place? M minus 1 L cube T minus 2. Here, first one, right? M minus 1 L cube T minus 2. 15th one. According to quantum theory, energy E of a photon of frequency F is given as E is equal to H into F. Then what is the dimensional formula of H? This I'll do it. Okay. So write down the equation E is equal to H into F. 15th question. E is equal to H into F. Okay, H is called as Planck's constant. You learn about this in atomic structure in your chemistry. Okay. 15th one. E is equal to H into F. So the dimensional formula of E is equal to dimensional formula of F into H into dimensional formula of F. So dimensional formula of H is equal to dimensional formula of E divided by the dimensional formula of F. Is that right? So what is the dimensional formula of energy? Energy and work done have the same units and same dimension. So it will be M L square T minus 2 divided by frequency. Frequency is the reciprocal of time. You know, frequency is measured in hertz, right? Okay. So frequency is actually 1 by second. So it will be 1 divided by T or T minus 1. T minus 1. So what will be the final answer? M L square T minus 1. So the dimensional formula of H is M L square T minus 1. Copy it. I hope you're able to do it. Right. 16th one. The dimensional formula of light year. So light year means distance traveled by light. Make a note. Light year means distance traveled by light in 1 year. So light year means we'll think it as time. Light year is the distance traveled by light in 1 year. Okay. That is the case. Tell me, what would be the dimensional formula of light year? Light year is distance. Distance, what do you use? L. So what is the option? C is the option. So you can also write it like this: M0, L1, T0. 17th. What is the dimensional formula of a solid angle? In dimensional analysis, I told you one point. You cannot find the physical. You cannot find the equation for physical quantities which are dependent on trigonometric values. So sine of, if you take an angle, generally you will get a value. So angle, you know there are two angles. What are they? Radians and steradians. So both these quantities fall under supplementary units, and for supplementary units you don't have any dimensions. So the answer would be M0, L0, and T0. It's a constant. You cannot write the dimensional formula. So dimensional formula is basically written only for the 7 fundamental quantities or the quantities which are dependent on those 7 fundamental quantities. Okay. So 18th one is also important. Read the question. The time dependence of a physical quantity P. So there is some physical quantity P. Here P doesn't mean pressure. Okay. There is a physical quantity. Oh, P is the pressure only. Okay. Here there is a time dependence of physical quantity P, which is given as P is equal to P naught into. There is something written as EXP, right? EXP stands for exponential. So means the meaning is P is equal to P naught into e power minus alpha t square. So generally, you know how you write exponents. A power m, a power n, you write it. No. You have learned this in your lower grades in your 9th standard. So a power m into a power n is a power m plus and all those things. Those are all exponents, right? This base, instead of a, if you replace it with a number called as e, there is a special number e about which you learn later. Okay, e to the power anything you write. This is also called as an exponent. Okay, minus alpha t square. So coming back, the question, the time dependence of a physical quantity P is given as P is equal to P naught into exponent power minus alpha t square, where alpha is a constant and t is the time, and P is what? Pressure. Now we need to find the dimensional formula of alpha. I'll do this problem. I want you all to listen to it carefully. So 18th one, P is equal to P naught into e power minus alpha t square. Is that what they are given? E power minus alpha t square is there. So listen, whenever you have exponential raised to the power of something, that power that is there, no, it is always a constant. I repeat it. Whatever is the power of an exponent, the power of an exponent is always a constant. So constant in the language of dimensional analysis means M0, L0, T0. Okay. Constant in terms of dimensional analysis means, or dimensional formula means M0, L0, T0. So what should happen here is, you're able to see two physical quantities on top of E. What are they? Alpha and T square. So alpha and T square are multiplied. So alpha's dimensional formula, so alpha into T square, can I call it as a constant according to the mathematical logic that I told you? So dimensional formula of alpha into dimensional formula of T square should be equal to the dimensional formula of a constant. What is the dimensional formula of constant? Right? So what is our job? To find the dimensional formula of alpha. So dimensional formula of alpha will be equal to M0, L0, T0 divided by the dimensional formula of T square, which is T square only. So what will the answer be here? M0, L0, T minus 2. So this is going to be the dimensional formula of alpha. Let's check if this is there. Is there an option M0, L0, T minus 2? Check which option satisfies. Option. Is it clear? So please make a note of it. P naught is a pressure at some temperature 0 or time 0, something like that. This is basically called as a function. Have you started functions in your school? Relations of functions. You know what is the next chapter after set, right? So it's called as a function. Clear? So this is one such problem. We'll do one last problem. Try the 23rd one. 1 gram centimeter per second is equal to x Newton second. 1 gram centimeter per second is equal to x Newton second. Then x is equal to what? So gram centimeter per second is in which system? What system of unit is it? Centimeter, gram, second. CGS. What is Newton system? SI or MKI system, whatever you call it. So do the conversion. So yesterday I taught you a method, right? So break it into two columns. Left side column will be in CGS, right side column will be in SI. Answer. Okay. So the answer will be x is 10 power minus 5. But did you understand what it is? The question given is 1 gram centimeter per second is equal to x Newton second. So x into Newton, I wrote it as kilogram meter per second square. Why? Because Newton is a measure of force. Force is equal to mass into acceleration into S. This and this will get cancelled. This is 1 gram centimeter per second. So either of the sides, I leave the values in terms of their original quantity. So what I did is gram, I tried to write it in terms of kilogram. 1 gram is 10 power minus 3 kilogram. 1 centimeter is 10 power minus 2 meter. Second is left as it is equal to x into kilogram meter per second. So this kilogram and kilogram are lost. Meter and meter are lost. Second and second are lost. So x will be equal to 10 power minus 2. It's a faster way to solve. So yesterday, whatever I explained was the procedure you need to write in your subjective paper. This is the way to find the relations between different physical quantities. This you can do it faster. Because as you progress, right, you'll see more number of physical quantities. This method will help you to solve things faster. Okay. So I hope it's clear, right? So with this chapter is done. Okay. So there are two updates. One is next Friday, okay, I want to conduct a test in this chapter. So during the class hours, you can come at 5 also, 5 to 6:30. We can have a test in this. And next Friday, I'm not available. Okay. So what I thought, maybe day after tomorrow, Sunday morning, can we have an online class where I teach you the basic mathematics, the slope, differentiation, integration? Can we have it this week? We'll have an online class. You need not travel all the way. Okay, I'll inform the timing tomorrow. So if at all I miss, then it is not there. We'll have it on some other day. If not, I'm just giving you a heads up depending on my timing. I'm not sure of my schedule on Sunday. So by tomorrow evening, I'll try to update. So be ready for it. Maybe 1 hour or 1.5 hour session we can have it where I'll be discussing about slope and differentiation. I'll not start integration. I'll discuss about slope and the differentiation and some problems that are based on it. Okay. That's it. Anything else I'm missing? Yeah. So two things: Friday test in this chapter, and Sunday hopefully we'll have an online class. Okay. So those are online. I hope you could understand.
Sir.
Yes. So yeah, be ready for the test and the class as well. So that's it. So any other doubts? Clear? So I'll share this worksheet. You can have a look at it. So any other problem also you can try solving from that. Okay. So that's it. I'll see.
Sir.
We'll wind. Yeah, tell me.
Sir, I'm trying to join from my institute, sir.
Okay.
And I don't know the organization code, sir.
It is epsilon.
Oh, thank you, sir.
Yeah.